Yes. Okay, great. Thumbs up. Thank you. Thank you for the welcome. Thank you, Jarek, for inviting me. So I'm Stephen. This will be a slightly different talk because I'm an academic. So I do build stuff. I build a lot of software. It's not production software yet. So I'm going to tell you some stuff about that I've been thinking about in the space of programming languages and, more importantly, programming systems. So I want to start by talking about two myths. And the first one is what I call the legacy myth, which is that whenever a new thing comes along, we get really excited. Maybe it's a new language, or it could be a new tool, or a new process, just a new way of doing things. We get really excited, and we think, great, we can throw away everything we've built and rebuild everything again, which never really happens. And to the extent that it does happen, it's not always a productive thing to do. So I rather think about it in terms of primitive tools, and the fact that primitive tools can still be used to build really great things. So that's why I showed you the picture of the Great Pyramid of Giza. So that's one myth that I want to take on. The other one is the myth that I call one true language. So I always think, wouldn't it be great if we can just make the best language ever? And then everyone will use my language because it's the best language ever. And then all those other nasty languages that people used to use because they were foolish will go away and the world will be wonderful. But of course, that doesn't really happen. So this is my symbolic view of having lots and lots of different languages, and we'll see why I chose a balloon in a second. So I'm going to say that although programming languages are great, there's something that's even greater, which is what I call programming systems. And I literally mean greater than programming languages in the sense of maybe including programming languages. So what do I mean by programming system? Well, here's one system I like to talk about. So this is Unix. This is Ken Thompson and Dennis Ritchie typing away in their teletype, connected to their PDP-11, developing the Unix operating system, or pretending to. So that's one system, and we can think of Unix as including a few languages. We've got the C language that's been part of Unix for a long time, since the beginning. Then we've got maybe the shell is another language that's part of that system, and then maybe you can think of the actual assembly language of your architecture as another language that's sort of in the mix there. So what defines the Unix programming system? Well, we've got programs, and then we've got processes. So we can write a program, then when we actually run it, it becomes a process. And we've got some tools that let us build a program. And then separately, we have this thing where we run it, it does some stuff, and we somehow deal in terms of bytes. So we've got memory, we've got files. They're all sort of unified as bytes. Okay, so that's one programming system. There's another system I like to talk about, which is Smalltalk. Okay, so that's actually developed roughly the same time as Unix, though people tend to see it as slightly later. So this is from Byte magazine in the early 80s when Smalltalk was sort of taking off, so to speak. And the very earliest versions of Smalltalk looked a bit like this. So they ran on a Xerox Alto, and they really were just what your computer did, right? So it wasn't that it was like a language that you hosted on top of an operating system. It was rather that this implementation of Smalltalk was in the firmware, in the sort of microcode even of the Alto. And that was just what your computer did. So and relative to Unix, it gave you a much more sort of advanced environment because you had a graphical environment, and you could also edit the program from within. So there you can see a window that's showing some code, and there you can just change the code that is currently running. So later on, different implementations of Smalltalk came along that were a bit different, and they were more sort of hosted on top of an operating system. So this is Squeak, which is still quite popular today, and this is Faro, which is another sort of contemporary Smalltalk environment. But those two have sort of moved away from the original vision because you do run them on an operating system. They don't take over your whole computer. So in the Smalltalk programming system, the program and the process are the same. So you just have an image, that's what you're working with. You edit the program as you go along. There's no separate sort of steps of compiling, assembling, linking, make it into a process. We do it as we run it. And we have a sort of higher level, slightly higher level abstraction that we work with that is basically objects and messages. So we have some sort of structured data with some sort of behavior and something like classes as well to sort of describe those objects as well. So if I sort of zoom out slightly and say, what is a programming system? Well, let's say it's two things. One, it's what it lets programmers do. And that includes the languages that might be available, implemented within the system. But it's broader than that. It also includes the act of programming, what mechanisms you have available to not just create, but also execute, debug, modify, and understand code. The second thing is what it lets programs do. So obviously the programs can execute, but they can also interact with each other. And that's partly realized by things like standard libraries that you do things like I/O, but there's actually a broader space of stuff that does that. There's, different primitive communication mechanisms. Maybe you have shared memory. You have some notion of linkage, which is what it means to actually load different bits of code and have them connect with each other. You may have some notion of foreign linkage, which is saying I've got some language, then I've got a space outside that language. And finally, you've got some sort of meta-level services, things like reflection or metaprogramming. Maybe you use them to implement debugging. Maybe you use them to build other tools. Maybe use them just to get a sort of overview of your code, or sort of write programs that deal with other programs in various ways. So they're all sort of facilities that I view as being part of the system, more than they are part of a language. Okay. My next slide will appear in a second. Right, so this is one of the creators of Smalltalk, Dan Ingalls, and he had this particular view of operating systems, basically that he wanted to get rid of them. So he said, actually in an article that was in that Byte magazine issue that I just showed you, he said, an operating system is a collection of things that don't fit into a language. There shouldn't be one. We should sort of eliminate all this operating system stuff. If we want to do I/O, if we want to do sort of any sort of thing that would conventionally be outside the language, well, we find a way to fit it into the language, and we do it the language way. Okay, so I personally don't like that view at all, and I'm going to be arguing against it for some of this talk. So what I'd say is that actually programming languages tend to be very opinionated. They have their abstractions, they choose their abstractions. The designer said, this is how I think is a really good way to build programs. And the design follows from that. And that means that there's always going to be competing views. There's always going to be lots of these things, lots of people saying, I want my language to be different. I want my language to be like this. Whereas if you think about an operating system of the kind that Dan Ingalls would actually be criticizing, one of the reasons that Unix has stayed alive so long and stayed current is that it's quite unopinionated. It gives you some pretty basic, pretty flexible primitives and lets you do whatever you want on top of that. And it doesn't really get in the way. Maybe you could argue with that. Maybe it does. So if we want to have this idea of one system, many languages, so we've said maybe having just one language is too restrictive, then we've got to be careful. We've got to make sure that whatever system is hosting these many languages can accommodate a lot of diversity. And that's diversity not only in terms of what languages you have, like what the language designs are, but also diversity in terms of how we implement the languages. Because another way in which people can come along and say, no, I know better, is to say, I can make a version of this language that goes much faster than yours, or has much better properties than yours in some other way. So we've got to have a system that accommodates diversity. And Unix is really good at that, mainly because it says, I don't care. You've got bytes, go for it, knock yourself out. So that's something we've got to be careful of. So this is my picture of how to do it wrong, which is that the Eye of Sauron, which is having one anything to rule them all, is a really bad pattern, right? Because you're basically encouraging people to walk away from your system. So if you have very strong opinions, if you say, well, this is something like the Microsoft Common Language Runtime, where they say, you've got to have our runtime. You can build whatever language you like, but don't try and innovate in that space of the runtime. There's only one true runtime. That's how we get all our magic properties, our nice interoperability properties. They only come about because we have one true runtime, one garbage collector, one just-in-time compiler. Yeah, maybe you can configure it or tweak it or give it different heuristics, but we've given you the one true way to do it. So that's something we need to avoid. And the reason we should avoid it is that if we try that, we end up basically having two systems rather than one. So if we do something like the Common Language Runtime or even the JVM, we always find them in practice sitting on top of a Unix-like system. The Unix hasn't gone away. Even the web, you have a sort of server-side environment that's basically Unix-like. You have a lot of configuration complexity that comes out of that. So what seems to be happening in practice is that we have these slightly more specialized environments that come along, but they tend to sit on top of a Unix, tend to build on it, and they seem in practice to include it. Like you can't, if you're developing on one of these platforms, you're always aware that you have some sort of Unix-like operating system underneath you. And by the way, when I say Unix-like, as far as I'm concerned, Windows is a Unix-like operating system. I mean, it gives you the same basic abstraction, slightly different names for things, but it's basically the same design. So this sort of 1970s design has really stuck with us. We try and build up from it, but we end up just including it. Okay, so my research has really been about saying, well, what's the path of least resistance? If we can't sort of get past Unix, can we just make it better? So one of the things that I've been working on to make Unix better is to make C better in some sense. And I don't really mean the C language. I'm not changing the C language, but I'm talking about implementations of C, how we implement C, trying to make it more debuggable, more secure, more safe in some sense. And secondly, I'm interested in how we can make the Unix process a better environment. So that means providing slightly richer abstractions, including making it better at hosting high-level languages. So if we implement a language, maybe like Smalltalk or Java or whatever we want to implement, how can we make it so that it's less of an isolated box sitting on top and more sort of integrated into the fabric that the system provides for us? So I'm going to tell you 3 little stories for the rest of this talk, all on that theme. One of them is about a dynamically safe implementation of C. I'll tell you what that means in a second. Another is about how we can have multiple languages in our system without having something nasty like what I call FFI. So FFI stands for Foreign Function Interface. And for example, if you use Java, then JNI is your FFI. Many different languages or language implementations have similar things. So they're very unpleasant APIs that make you write some glue code that you'd really rather not write. So rather than having that in our system, it would be nice if we could do something else, in particular evolving the notion of memory as bytes that Unix gives us into something that still can be bytes if we want it to be, but is also richer, has a bit more structure, a bit more semantics. And finally, if we really want to get rid of FFIs and things like that, and also to add a lot of sort of dynamic services, kind of Smalltalk style live programming to our system, we're going to want to have something that's a bit like a garbage collector, but it's not one garbage collector. We're going to have some foundations that let us build many different garbage collectors inside our system. So I'll come on to that towards the end. So here's my first story about once upon a time there was a language called C. It was very popular, very successful, but after a while everyone started calling it names, saying it was unsafe, saying it was dangerous. But despite that, they still use it to do a lot of stuff. They still depend on it all the time. So that's the situation we're in today. A lot of people complain about C, but somehow we haven't got past it. So why do people complain about C? Well, this is a really nice illustration. It's by John Reger from the University of Utah. So he wrote this little simple example program. It's just doing an addition, testing whether that results in something less than 0, and printing out the answer, the result of that. So either 1 or 0, because Booleans can be converted to integers. So we're going to, hopefully, we're going to run this program. It's going to tell us either 1 or 0. But unfortunately, it's a perfectly legal implementation of C to do something like this. We run the program, and it starts formatting our root partition. Yum, yum, yum. Away goes all your data. So that's perfectly legal in C, because C has this notion of undefined behavior. And we've actually managed to invoke undefined behavior in this program. Anyone know where the undefined behavior is? Yes. The person who put their hand up. Right. Well, that's interesting. That's currently how it's used. Right. Compiler guys say, great, the behavior is undefined. So what I do is I assume that whatever condition makes the program undefined, I assume that's not true. And then I optimize. That's an extra input to my optimizer, and I optimize based on that. So in this picture, where is the undefined behavior? Right. So signed integer overflow, which is when we do int max plus 1, is actually undefined in C. And that's because there are many different machines, all might have different behavior on overflowing of a signed integer. So in order to keep the language portable, we say, well, we don't really, there's nothing in particular that could happen. Anything could happen. It's an error if you do that. And we don't say what happens when that error occurs. So I'm going to just do a quick demo where we take a couple of different implementations of C and do this. What do we want to include? Include limits.h, independent void, int f, int max plus 1 less than 0, and then return. Does that look all right? Okay, so let's try that. So I'm going to use GCC overflow. Overflow.c. I'm going to turn on debugging just for fun. Excuse me. And I'm also going to turn on optimization. Yeah. Okay. Okay. The compiler's been nice and told us that it could statically detect the warning, but we can still run the program, and it gives us an answer. So it was allowed to give us any answer, or in fact do anything that it wanted. It's been nice and basically just made the arithmetic wraparound. So it does give us something less than 0. Okay, so, but because we have a lot of freedom in how we implement C, we have some, you can use a different compiler. let's use a different compiler, and let's turn on a particular option called trap-v, and that's actually going to be a much nicer implementation, because although it's allowed to do anything, in this case it chooses to do something which gives us some kind of trap. So the point where we did the addition, it gives us a trap. But in fact, if we run it in the debugger, and I'm going to make sure we get the signal, oops, when it happens. So we can run the program, and indeed we've got a nice clean exception at the point where we did this overflowing addition. So that's much better from a debuggability and a security point of view, because at the point where we did the bad thing, rather than letting our program carry on and do arbitrary things, which could in some circumstances be a security risk, we instead give a clean trap. So we've explicitly stopped the program cleanly at that point. So that's sort of telling us that the safety of our language is actually a property of the evaluator, so the implementation of the language. And this is something that you can find if you dig around in the research literature. It's sort of reasonably uncontroversial if we think about it, that whether we have safety or not is really a property of the implementation of a language. So a program that works properly has the same behavior on an unsafe or a safe evaluator, but it's when something goes wrong. So it's in this snippet we're saying misinterpret some data, so this would be doing integer overflowing arithmetic. The problem is that we can't predict how it behaves under an unsafe evaluator. So safety is always somehow about predictability. Even if we're interested in static safety, so like static checking, that's really, again, a kind of predictability. We're saying, I really want to know whether this program might go wrong. So can we have a safe evaluator for C? We've just seen sort of one instance of making an evaluator for C that is safer by having this sort of trap mechanism. So let's look at something a bit more complicated. This is using pointer arithmetic in C, which, which many people say is, a very dangerous feature. So here we're taking a pointer to an integer, we're adding some offset to it, and the language spec says, well, after you've added the offset to the pointer, you better make sure you're still pointing into the same array you started with. If you're pointing somewhere else, then that's not okay. So we can read that in the C language spec. It says, well, if they point to the same array object, there's also a special case of one past the end. And that's so we can make a sentinel pointer if we want to. So that's okay. Otherwise, undefined behavior. So if we get it wrong, then at this point, anything could happen. Or maybe even at this point if we get it wrong. So we're completely allowed. I suppose the point I'm making here is that C is not specified as you must be unsafe. It's that we don't require you to be safe. So it's a perfectly valid implementation of C if we did something like this, where we did a translation, where we actually explicitly check. So let's imagine the compiler is internally translating our code to some sort of check that says, well, if we do end up in the same object, then that's okay. We carry on. We do what we were doing. If not, then we generate some sort of special magic trap value. And that's going to give us some sort of clean exception, just like in the overflow case we just saw, if we actually use that bad value. So people talk sometimes about having maybe we need a subset, we need a safe dialect, a safe subset of C, but actually we don't. In this case, we have exactly the same language features. We have the same set of valid programs. We have the same set of behaviors in executions that don't contain errors, and we have a narrower set of behaviors if we have some sort of error behavior in our program. So it's not a subset, it's not a dialect, it's just a refinement of the actual spec. It's what the language lets us do already. We don't need to define some special dialect or subset. Undefined behavior is freedom to refine. We can decide to be safe if we want to. So I'm going to show you what my compiler, it's not really a compiler, it's just a wrapper around the normal compiler. So let's check I don't already have a file. Okay, we're going to make a really stupid buffer overflow program. Oops. And what's it going to do? We're going to have some array, and then we're going to print an element of the array, and we're going to go out of bounds. So let's go out of bounds by 2. So we're clearly out of bounds. And if this demo works, then we're going to use my implementation of C, which is somewhere in my repositories. to compile this code, we're going to turn on debugging. We're going to generate buffer, and we're going to optimize. Whoops. Should really fix that warning. Anyway, it's compiled it. And then we're going to run it, and we have to run it with my special runtime loaded. So just check we got the file. Yeah, okay. So we're going to preload another binary. This is my runtime called libcrunch, which is the name of the project. And if we run it, fingers crossed, did I get that right? Whoops. Right, so it's given us a somewhat cleaner warning saying, at the point where we derived a new pointer, we had a check that failed. So we were supposed to be within this particular range of values, like this was our array between these two addresses, LB and UB, lower bound and upper bound. And instead we derived some pointer that was outside that range. And it tries to carry on in development mode. You can turn it so that it aborts. If you're in a production setting, you probably don't want to carry on execution after something like that. But you can also have it so that it carries on. And it actually generates a pointer that if you use it, it will cause a trap. And here the trap is actually in a SegFault. And this output is a little bit nasty, but it's basically a SegFault handler trying to explain what just happened. It says, well, possibly an invalid trap pointer was used. So we got a hard stop rather than a corrupting failure when that thing happened. So if you're familiar with tools like address sanitizer, you think, well, what's the difference here? Well, this tool is actually much more precise. So it's checking much more closely. It doesn't just check whether you're roughly within bounds. It doesn't have some sort of approximations. It's really checking very precisely. And it has vaguely competitive performance, although it's currently a little bit slower, but it's going to get better. So that's just a quick view of the libcrunch project. I'm going to move on to my second story, which is about memory as a shared abstraction. So we've just seen that we have undefined behaviors that are about memory, and they're actually the trickiest ones. They're really quite hard to check, quite hard to detect statically, because it means that our execution is defined if some property of memory right now holds. And memory is always changing at runtime, so it's hard for the compiler to do very much about that. So we had this instrumentation that's checking logically whether it's in the same object when we've done our arithmetic. And we clearly have to have some dynamic model of memory in order for that checking to be possible at runtime. So that's one observation. But there's another observation which I'm going to claim is related, which is, well, I'd say, why doesn't C have some sort of FFI? Like, what is it? What's special about C? Why is it not like these other languages? Because it turns out that C just gives you memory, and that's it. Memory is the main abstraction of C, and it's done in such a way that you don't need any kind of separate concept of foreign memory. Memory is just shared in a general sense, and that's sort of very much at the heart of the C language. So let's move on to see what that means. This is a little bit of code. This is actually my code. It's just a simple loop that's walking over some memory. Turns out this is code in the runtime that was running the example we just saw. And all it's doing is iterating over some memory with a simple cur pointer. And it turns out that this memory contains instructions, so instructions in our running program. Turns out that to implement some of the stuff I just showed you, I have to occasionally rewrite some instructions. So I have some loop that will iterate over those instructions and call a callback on them, in some cases at least, and then increment my pointer accordingly. So what's interesting about this is that this can walk over any instructions in your whole program, whether or not your C compiler knows anything about them. So it's really accessing memory that is potentially not part of your C program at all, but it's using the core abstractions of the C language to do it. Right? So as far as the C language is concerned, there's no special kind of foreign memory, there's no external memory, there's just memory in your address space, and we can use the core features of the C language to access it, which when you think about it, it's pretty unusual. So programs abstract over memory, and that can be stuff that's defined in C. The memory could be holding my C program variables, maybe my globals, maybe my stack, whatever it is, or alien memory. That's what I'm calling potential other memory that happens to be in your address space. And we've got the same language features abstracting over both. Another way of putting that is that alien memory is first class. Right? First class memory is what we have. If we can do all the normal operations on a thing, we're used to saying things like my language has first class functions. Well, in C we have first class memory, including alien memory, and that's why we can get away without having any kind of FFI-like thing in the language. So why do I use the word alien? Well, I love this quote. This is by JCR Licklider, who many people have can claim to be the grandfathers of the internet, but this guy had a pretty good claim, I think. So he said that if we succeed in making an intergalactic network, which was his slightly jokey name for the internet before people used the word internet, then we'll have this problem, which is communicating with aliens. So we'll have more and more code from more and more diverse places, and more sort of heterogeneity, and we're going to have this real technical problem of bootstrapping meaning in this very sort of diverse environment. So I think that's exactly what we have now when we have, increasingly many languages, increasingly many sort of varying ways of doing basically any programming exercise at all. So one of the interesting things, again, just interesting thing that you can do in C that is kind of a bit mind-boggling is that you can get your memory from outside C if you want to. So I can call an allocator that I've written myself, and it could actually be written in a totally different language. It could get its memory from a mechanism that neither the C library nor the compiler nor anything in our toolchain actually knew about, and we can still generate our ordinary C code against those objects. So in a sense, custom memory allocators are sort of a testament to the fact that this design of memory is actually a very powerful one. Okay, so let's contrast that with something else. This is some really stupid C code, almost not worth bothering writing. Maybe want to use this code from some more modern environment, like maybe JavaScript or something. So how can we do that? Well, this is, if you ask the V8 developers, this is a few years ago, but it's probably not changed very much. If you ask the V8 developers what you should do in order to use a simple pair of ints structure from your JavaScript code, well, they say just write this. And by the way, this is just for the X field. I haven't even got on to the Y field yet. So this is just a getter for the X field, getter for the setter for the X field. So that doesn't really seem tenable. Like, why should it be so complicated to access something so simple? And of course, it's because of this myth, right, that says, well, we've got this JavaScript thing now. It's going to be the best. So no one's going to want to do any of this legacy stuff. So it's just going to be, well, we'll give you some way of doing it. We'll use it, when we need to, but basically that's not important anymore. So if we want to get past that, if we agree that that's not a good way to go forward, then we want to build some sort of memory-like abstraction that, again, is this sort of shared thing. Many language implementations can share this, maybe. We have to think system, not language. So I'm going to show you my answer, which is embodied in the system I demoed to you a minute ago. It's called typed allocations. So we start by saying, well, the memory in our process is not actually just completely opaque bytes. On a modern Unix, we can ask the operating system to tell us something about what's in our memory. So this is what happens. This is a Linux-specific interface, but there's similar things in all the BSDs and so on. You can actually do some kind of reflection where you say, well, what's in my memory? So this is a cat process inspecting its own maps file, and the maps file is how the kernel exposes to you what the contents of your address space is at the top level. So you can see there's nothing for the first quite a lot of addresses until we get to this 5.5 sort of range. And then we've got some mappings. This is saying, well, it's actually a mapping of your executable itself. So this is the text and the data of your cat executable. And then you've got a heap region, and then you've got a mapped file that's something to do with the locale support in the C library. Then you've got the C library segments. Then you've got some anonymous section that's probably another kind of heap-like area. And then you've got the same thing for the dynamic loader, that's this LD thing. And then you've got the stack, and you've got a bunch of other things that the kernel puts there to help us make system calls. So we can actually sort of group those items, because some of them are kind of related. So some of these mappings are just there. They're basically contiguous mappings, but they happen to have different permissions. So they get a different row in this table. But we can group them. That's why I've given each group a different color. We can say, well, this is the text segment for the cat. This is the data segment. This is the heap, and so on. So we can view that as a sort of tree, where the top level of the tree, the root node, is saying, what's the whole address space? And then we can say, well, our address space is divided up into these sections, these different chunks. And the first one is the text segment, and then we've got a data segment, and then we've got a heap arena, and so on. And these are a tree because this subdivision keeps going, right? So we can, underneath, maybe we've got in our heap arena, we've got a malloc chunk. And then maybe we've got our own allocator that works by taking a big chunk from malloc and then dividing it up even further. Or similarly, we've got a stack here. This is just a sort of mapping, memory mapping. But within our stack memory mapping, we've got some stack frames. And then within our stack frames, we've got our individual variables and so on. So we can think about this as a sort of recursively decomposed sort of substructure, which terminates in our program variables. So the leaves, where it terminates, they're places where we can hang off some sort of type information. So maybe we've allocated a chunk of memory, maybe like our point in the previous example with the x and y coordinates, and we can actually attach some type information to the leaves of our tree. So what does that type information look like? Well, in my implementation, this is a slightly simplified view, but if we have a slightly more complex structure, now with 2 levels of structure, what we end up getting in our runtime are these descriptors called unique types, and we have one for every distinct type that happens to be in our program. So here we've got one for int, one for double, one for point, one for ellipse, and they describe the substructure of those types. So here the int is this first saying it's 4 bytes, and it happens to have no sub-objects, so no substructure. And then we've got a double that's 8 bytes, and actually in the real version there's some more fields here to actually tell you what it means to be an int, like what is assigned to complement encoding and stuff like that. But this is just showing the substructure. I see, well, our point is, sorry, it should say point there. I missed that out. Our point is a 16-byte thing. It's got 2 sub-objects. One at offset 0 is a double. Another at offset 8 is also a double. And similarly, ellipse has 3 sub-objects. The first one is a point, and the next, sorry, the first 2 are doubles. The next one is a point. So we've got these descriptors, and they also describe things like functions and enums, and there's some dynamic things that actually change their layout. We can describe them as well. And one place that all this information comes from, you can generate it from lots of places, but one place it comes from is from the debugging information that the compiler generated. So when I did my when I ran the compiler earlier, I was careful to turn on debugging information. And if you look at what comes out in your compiler's debugging information, you can use this handy readelf tool to do it. And it's actually really, really detailed. It's really rich information. So here it's telling us that, well, we had a compilation unit called hello.c, and it has this particular range of addresses that it comes out as in the binary. And it's got a type in it called int, and that int is 4 bytes of the signed encoding, signed to's complement. And we've got a pointer type, and that's also got some byte size, and it points to some other type, and so on and so on. So we've got a lot of rich type information there. We've also got information about the local variables, or in this case, the formal parameters. So here we've got something saying, well, in the function main, we've got a formal parameter called argc, and that lives at a certain place in memory, right? It lives at 20 bytes away from this thing fbreg, which means the base of the stack frame. So wherever the stack frame of that function is in memory, well, we find argc 20 bytes away. So we've got a very rich source of information there. So one thing that I've demoed in the past, actually I broke it recently, so I can't demo it for you today, but it's a hacked version of Node.js that uses this extension. This is called liballocs, the sort of the runtime extension that maintains this view of memory, and you can do some quite cool stuff with it. So instead of saying we need to write some nasty glue code in C or C++ to import new stuff into our JavaScript environment, I just said, well, no, I'm just going to use my runtime metadata, and I'm just going to hack the VM slightly so that it has this new object called lm. lm just stands for link map, and it means any function or object that is visible to the dynamic linker, so it has a symbol, a linker symbol at runtime, it's just going to appear in this object as a property of this object. So we've got printf, right? Printf's visible to the dynamic linker, so we can just call it, and it will do that, and it will print hello world, also tell you how many characters it printed, because that's the return value of printf. And then we can do some more funky stuff, so we can actually dynamically load some more libraries, because dlopen is itself a dynamically visible symbol. So this is just a syntactic sugar around doing a dlopen, a dynamic. Like if you were loading a plugin, let's say, it would be doing exactly the same thing. And because I like old school X11 programming, I wrote a little program to basically make a little X11 window on the screen, and then if you click it, it exits the program. So it calls the exit method. So again, that's just exit function in the C library. Just going to call that as a callback. So the way to think about this is it's not like a magic gateway between JavaScript and C. It's that I've actually got this rich notion of memory that actually gives us one object space, if you like. There's one space of objects in the whole process, and many different per language views. So obviously the next step is to hack this guy some more, so that JavaScript objects could also be exported in that way. That doesn't currently work, so don't go crazy, but it will eventually. So that's the sort of concept that I'm going for with how to get rid of FFIs. Okay, so the last story I'm going to tell, if I've got time, yeah, I've got a bit of time, It's about, we've seen the substructure, right? We've seen that memory has this substructure that sort of terminates in some kind of type information, but we've got this other problem, which is we want to know where all the pointers are in our whole process. And that's so that we can do stuff like garbage collection, but maybe we want to have many garbage collectors, each responsible for different bits of our address space. And maybe we want to have some sort of Smalltalk style liveness, some ability to really change stuff during execution, even for C code, right? So it's not part of the language, not part of the C language, but it doesn't mean we can't have it as part of our system. It doesn't mean we can't have some sort of live programming, ability to redefine stuff as we're running. And if we can do that, then we can really, I think, eradicate FFIs and a lot of the reasons for them, as well as doing a lot more cool stuff. So there's some good news, which is that Unix already knows where the pointers are. This is a bit obscure, but turns out, I'm going to show you something. We can have a hello program. Have I got a hello program? Hello.c, I should do, yeah, okay. So if I build hello world, I'm going to do a static linked version of it. What else? Turn on, actually not going to turn on debugger. Okay, first I'm going to look at hello.o. So one way in which we can see the pointers is that obviously that we can ask this nice objdump tool to show us what's in the compiled code. And actually, it knows that there's some pointers that need to be filled in there, right? This is what the linker is going to do for us. So in this case, we can see that it knows that there's a field inside this instruction that's currently zeros, but we're going to have to make it point somewhere into the RO data. And that just means it's actually pointing at a character string. So this is the hello world string. There's some address that string is going to have, and we're going to fix up this instruction so that it actually points to that string. And similarly, we've got one that's going to point. The compiler was very clever and turned my printf into a putS because it can do things like that. But anyway, it's going to make this instruction, the actual call instruction, point at my putS once we know what address that's in. So it basically knows that these chunks of instructions are actually pointing somewhere. And it turns out that if I do actually build my static thing now, and I'm going to just add a little switch to the linker to keep the relocation information around. And it turns out you can't get objdump to give you all the information in one go, so I'm going to use my handy script that I prepared earlier to do this. It takes a few seconds to munch through everything. But we're actually going to see that we can see where the pointers are in our data as well. So it's not just the instructions that have relocations. It's also data. So we'll be able to see where all the pointers are. Here we go. So this is just a binary dump of the data in our program. We can see that we actually know that, at this particular address, whatever it is, 6A25B8, there is a pointer. So this label here just says it's a 64-bit pointer value. So the other ones are 32-bit PC relative, and they had a slightly different string here to represent that different encoding. So we have a generalized notion of pointers. So that's kind of good. We know something about the pointers. But there's a problem. We only know about where the pointers are when our program starts. So once it's actually executed for a while, it's written some new values somewhere, it's used to stack and registers to hold some stuff, then we don't know anymore where the pointers are. Except, well, we've already done a bit better than that, because we saw from my example earlier that we can actually inspect memory. We can get type information for arbitrary memory. And in fact, inside GDB, when I'm debugging stuff, I actually often do this. My runtime has a nice handy call. You can just ask it, well, I've got this pointer. I don't know what it's pointing to, because statically in my program, it's just a void pointer. But maybe you can tell me what it points to. And here it's giving me the descriptor, the type descriptor, the kind I showed you. And this happens to be the descriptor for pointers to a 32-bit integer. So we've already got some runtime type information that can help us, because it knows something about where the pointers are. And then we can use that. This has allowed me to inspect the memory in a way that I couldn't if I didn't have that. So that's good. But there's a problem, which is it doesn't actually cover everything. So if we post-process our debugging information, so the stuff that I showed you where we had the debug info for main, and we had some information about the formal parameters of main, well, we know something about, in our stack frame of main, we've got a pointer to assign chars, that's our argv. We've got an int, but we've also got a kind of hole, like there's some range of offsets. There's 4 bytes here between offset 8 and offset 12 that we just haven't accounted for. So in general, we might have holes here. So these are things that the compiler just didn't bother describing to us in the metadata. And it might be that there's some pointer lurking in there. Like maybe it's a temporary that the compiler generated for us. So we've got to worry about how to deal with these holes, how to maybe get more complete information out of the compiler, or how to live without the compiler actually giving us that. So what I'm working on right now is actually doing something a bit like what Linux is doing to get around a similar problem. So in Linux, recently they added a tool called optool that actually walks the instructions that come out of the compiler, and it figures out what it's doing with the stack pointer. And it turns out that's necessary in order to reliably unwind the stack. So you got something going wrong in your kernel, you want to print out a backtrace. Well, if you just rely on what the compiler tells you, sometimes you can't print out the backtrace. And so we write a tool, the Linux developers wrote a tool that literally walks through the instructions in your binary and figures out exactly what they do. So it gives you reliable information. So the goal is here to do the same thing, but keeping track of which stack slots and which registers are holding pointers. Same idea, just a slightly different tool. So that's hopefully going to give us a much more reliable set of pointer metadata than we would otherwise get. So there's many things in progress. I'm going to wrap up now. One of them is this pointer metadata tool. Another is if we can do some sort of, if we can know where the pointers are, then we can do some sort of temporal checking for C, which I didn't show you because it's quite hard, actually avoiding things like use after free without paying a lot of runtime overhead. We can also do some sort of liveness to actually dynamically change things, and if we need to reallocate them with a bigger size and change all the pointers so that they now point to this new thing, then we should be able to do that. Retrofitting some more VMs, so I have my Node, my hacked version of Node with the hacked V8 inside it, but I want to be able to do some more languages, maybe starting with one that's a bit less unpleasant than V8, because hacking V8 is quite nasty, and making the whole thing faster and more robust. So that's sort of plenty of ongoing work to be done there. Okay, so thank you to all the people I stole pictures from online. I promise that was totally legal. They all said I could do it. And finally, I'm going to conclude. So I'm going to claim that systems are greater than languages, literally, and in maybe a few other ways. And that dragging Unix forwards, sometimes I joke that I'm dragging Unix into the 1980s. It's like giving it small talk like abilities, like, wait, it's 1980 again. But it might be our only hope. I honestly think that we can have a much richer, more well-integrated infrastructure if we take this approach. So I've got a load of code on GitHub. All the stuff that you've seen is on GitHub. Thanks for your attention, and I can take questions.